Kanak, can you hear me?
Yes.
Yeah, I think so. We can start the lecture. It's already 10:03.
Okay, not an issue. Okay, thanks. Good morning, everyone. So, yesterday, when we sort of finished our class, I think I talked about this slide, and that's where I stopped. And the message that I give it to you is that the stars do not do any head-on collision in a galaxy. Okay, and the um, apart from the since the gravitational force is long-range force, so even if there is no head-on collision, there will be encounters. Like one will try to deflect one star will try to deflect the other, okay, through its long-range gravitational force. And such the deflection can be like the strong deflections or weak deflections and things like that. So one can estimate the impact of the strong encounters. For example, a star is said to have gone through a strong encounter when the change in the potential energy is at least as large as the kinetic energy. So, for example, imagine like the R collision is like the closest distance, which is like 2 gm over v square. M is the mass of the star, and half mv square is the the kinetic energy it carries. Okay, so then from this one can think about the characteristics time between collisions, which is like 1 over the number density of the stars, the cross sections, and then the v is the velocity. Okay, so it turns out that this collision time is also like much larger than the Hubble time, which is like 10 to the 13 years or like more, depending on some density, velocity, okay, and the mass of the stars as well. So we don't need to worry about the strong encounters as well, as long as that we are within the Hubble time, say. Okay, then there is something else which becomes much more important, because they say, okay, the head-on collision is not important, strong encounters are not important. How about the small deflections? Okay, the small deflections will keep on maybe adding up. So it turns out that these calculations of the small encounters such that let's say one star passing by to another one here, and they would slightly deflect the stars in the vertical directions, because imagine the stars would go on a horizontal along the horizontal, is it some cross sections of the orbit you can think about. Okay, so then the stars will go in the horizontal, but because of this another star which is sitting down here, so this will try to deflect in the vertical direction. Okay, and then along the orbit of the star, okay, many such deflections can occur. All right, so sometimes it can, and then the deflections this can be sort of randomly oriented, and then if you sum it up, basically the total would go to basically zero, no net change, it seems. So so but if you add it up in terms of a square, so imagine delta v perpendicular is the small delta change in the vertical directions, the velocity change. Then you can sort of do the sum of this squares, and say, okay, and integrate over all the stars in the system. Okay, so integrate over all the stars in the system. So I am not going into the calculation, sorry about that, because I think this is a bit lengthy. So it is something very much like your Coulomb logarithm, the integral, so this is the actually event that is the one will come. If you are curious, you can look into Binit Remain, and if you have any questions, I will be happy to answer you. So not an issue. So, but what is like, what you learn from this is that, like, so these small deflections, if you add it up in the, like, the squares, and over a longer period of time, over say time period t, then the total change in the velocity may be equal to the original, like, the velocity square of the star. Okay, and that is the time, that time is called the relaxation time. And if we calculate the relaxation time properly, it seems like it depends only on the number of the stars in the galaxy and the crossing time. The crossing time is basically your um, r, which is the size of the system, the size of the galaxy, and v is the mean velocity. Okay, so mean velocity. So imagine, like, you have a Milky Way, and the Milky Way stellar disk is 15 kiloparsec size, is a radius, and the typical velocity of the stars with which is going around, so it could be, let's say, like about 200 kilometer per second. Okay, so you can easily calculate the what will be the crossing time, okay, in a galaxy. So that's the thing. So the crossing time, and it depends on the number of particles or number of stars in whichever way you like. So, and we have already, like, sort of shown in the 2 slides before, is that the number of particles or number of stars in a galaxy in a naively calculated way is like about 100 billion, so 10 to the 9. And the crossing time is typically, like, more than, like, a few 100 million years or million years, depending on the system. Okay, because it's the r cross r divided by v. So you will see this t relaxation is absurdly large. Okay, so there are some approximations, there are, like, these things, but, like, essence of this is that the relaxation time is very large compared to the Hubble time. Okay, 10 to the 11 multiplied by 10 to the 8, so 10 to the 17, some, like, the years, which is like a lot. Okay, so what it turns out that, like, there are system, for example star cluster, in which the number of stars are basically around 10 to the 5, 10 to the 4, maximum 10 to the 6. Okay, and the crossing time is also very short. Okay, the crossing time is like about the size of a star cluster is about a parsec, few parsec. Okay, and you divide by the, like, the mean velocity, which is could be around 30-40 kilometer per second, and the t relaxation turns out to be, like, much sorry, not much lower, but it's less than the Hubble time. And then in that in the star cluster, the stars may actually be affected by this relaxation process, by this, like, two body encounters that we have talked about just now here. So these two body encounters, like, as I said, like, for a galaxy like system, like, take an elliptical or spiral, they are not very important, okay, within the Hubble time. But this becomes important for a star cluster, globular cluster, things like that, and easily you can verify this. Like, you can go to the t relaxation calculations and put in the numbers there, and you can easily, like, check. And this the origin of this calculation is actually written, like, very elaborately in a paper by Chandrasekhar in 1943. So it turns out that the head-on collisions are not important. Both strong and weak encounters are not important during a galaxy's lifetime. Okay, so we can be, like, safe from we can be, like, safe to ignore the effect of these two body encounters in a galaxy. Okay, it turns out, like, very, like, if you look at the galaxy, I mean, it's not very, if you start thinking, it looks like simple, because it's not very complex, because as you see, like, the nearest neighbor is like 1.3 parsec away. Okay, the stars are don't, like, mingle each other in a galaxy. So this is not the place for that. So essence, in a way, is that the galaxies are basically, the collisions are not important. Okay, the galaxy can be considered as a collisionless system. So that's the kind of like the message. So just to recap from this slide, we have talked about what are the things we talked about. We talked about the different types of galaxies. Then we talked about the how the light distributions are like. What is the light distributions in a galaxy? Okay. Sort of like we saw that in a spiral is like light like the distributed in a exponential function with a scale length and the central surface brightness. And then also in an elliptical galaxy, there are well-defined where the light is distributed in a elliptical galaxy. And then I think we also talked about the gas distributions in a galaxy. Okay, so there are neutral hydrogen gas. What are their extent? Okay, how far do they extend, like compared to the stars? Okay, and how we can use the neutral hydrogen gas velocity through the 21 centimeter line measurements to the measurements of the this is the most one of the like the most important indirect evidence through which we know about the dark matter in galaxy, the rotation velocity and its explanation. Okay, and so that's the kind of like thing. And then I think we talked about the briefly about the cusp core conspiracy about the dark matter halo. And finally, when we know all the compositions of the galaxy, like the what is the galaxy made up of, what are the different light distributions in a galaxy, so we are now in a position to talk about the motion of the stars. Okay, so because we sort of said that the 90% of the like the matter, baryonic matter in the galaxy is made up of stars. So only 10% in some sense light. But then I said also that there are galaxies in which the gas fraction or the amount of gas is much more than the 10% typically in the Milky Way like of galaxies. Um, and then so having understood like a bit of that, and then we sort of said, okay, how do the stars move? And then we now understand that the stars are actually moving in such a way that they don't do collision. That's an important message. And then the stars are like collisionless, like sorry, the galaxies are collisionless system in some sense. And if we have understood that, there is a lot of advantage of that. I like stop sharing this, and then I will like start sharing my second slide. Just give me a second. um, can you see the screen?
Yes, sir. Go ahead.
Okay. Okay. Now I'm going to talk about basically the motion of the stars in a galaxy, because the idea is to basically to go towards the like the dynamics. But before that, like we must know, but we know the distribution of light in a galaxy, so you want to know how the stars are moving in a galaxy. So the one of the advantage of like going to sort of understanding galaxy as a collisionless system is that you have a tool to explain the galaxy. So it's bit advantage the advanced like stuff, because I'm not like going to go into like a lot of details, but I'll just explain in one slide. Is that that once you say the galaxies are collisionless system, there are ways to like the understand the physics in the galaxy, and that's where like the collisionless Boltzmann comes into picture, collisionless Boltzmann equations. And this is where the collisionless Boltzmann equation, and so understand this. So this is the collisionless Boltzmann equation, which is basically nothing but the it's an if you look at this equation, it looks like this is the del f del t. Okay, so it's a partial differential equation for a quantity called f. F is nothing but the distribution function. Okay, distribution function of the stars. Distribution function is a function of the phase space variable, which is the r, which is, you can like think about the Cartesian coordinate x, y, z, and the v is vx, vy, vz. So it's a like 6-dimensional phase space, okay, in which like you define a distribution function. Okay, the distribution function, if you integrate over all velocity, you basically get the number density. Okay, in other words, in a small infinitesimal volume, which is d3r and d3v, you will get the, if you look at the number of the stars, which is like a dn. So dn divided this infinitesimal volume, and is basically like, can be written in terms of a, like the distribution function. And in essence, like as I said, if you integrate, you basically get the get the number density of the stars in the system. And once you have written a distribution function, which is depends on the phase space variable, and then these phase space variables like the r, the position coordinate, and the momenta or the velocity, if you like, then they are actually connected through the Hamilton's equation of motion. Okay, so you can write down the Hamilton's equation of motion, and actually, like, you can say that r and v. So basically, under that, like, say in this the collisionless Boltzmann equation, the Hamilton's equations of motions are inbuilt in some sense. Okay, if you so that's the collisionless Boltzmann equation. Okay, the collisionless Boltzmann equation also, like, have a, like, you can, like, I mean, I don't know, one can, like, talk about, like, a few classes on this collisionless Boltzmann equation. So it is not so this is, for example, on the right side you say, like, this is 0, because we have in while deriving the collisionless Boltzmann equation from, like, what is called the BBKG hierarchy, we have neglected uh, the um, the collision term. Okay, the collision term, the in other words, like the particle, like, can actually interact with each other, and there can be certain, like, the correlations. So if you think that the one particle's motion is independent of the other particle motion, then one can actually, like, sort of neglect that kind of correlation term and the collision term, and basically end up getting a collisionless Boltzmann equation. There's another important fact that you must know, just to begin with, is that the distribution function is a distribution function of one star. Okay, this is not a distribution function of n star. Like when the BBKG hierarchy, like, the stars in the very beginning, you write the distribution function of n stars. So in other words, this argument here, which is r and v, it will be r1 r2 dot dot rn, and then v1 v2 up to, like, dot dot vn. Okay, so it's an n particle distribution function, and then we say, okay, like, from the n particle distribution function, actually, like, comes to, like, one particle distribution function. And this is possible only when the stars in the motion is, like, not correlated with the other the presence of the other star. So that is why basically that is the one key thing in deriving the collisionless Boltzmann equation. And apart from this sign, which is like apart from the sign in the potential, this is exactly same as you see in the plasma physics, for example. Okay, and the collisionless Boltzmann equation, you see this first term here, which is the gradient of phi. Phi is the potential. The potential is basically connected to the Poisson equation, and then again the density rho is actually integral over f d3v. So in other words, this gives you complete information. The Vlasov-Poisson system, or the collisionless Boltzmann Poisson system, it gives you the complete description of the of an isolated galaxy. Okay, isolated the galaxy, and this equation is basically an integral differential equation, and it's like very difficult to solve, but you can try. There are methods. There are Fourier transforms. One can do Fourier transform, for example, through Fourier transform and Laplace transform. One can actually get some lot of insights about the wave mechanics here. For example, how the waves and the particles like interact, and there's a one change here, which will be the gravity, which is the sign change compared to the plasma physics, and that brings a lot of change in the system. Although this is a very similar system in terms of this thing, but except that the force is very different. In plasma physics, you have a shielding. In gravity, there is no shielding. Okay, the gravity, nothing like stops like the two stars like they're coming arbitrarily close to each other. Okay, so that's a kind of a problem, and one there is, so in other words, because we don't have any screening like a device shielding like that, so it becomes a very difficult the issue to there are various things like the various like troubles comes into like solving this equation. Nevertheless, people started doing the direct integration of this equation as well. So if you're interested, like go ahead and look. The other ways of like looking at, of course, like you can write down the like there is a n particle system here, which is like we have like n stars, and then you calculate the potential due to the another rest of the system. So basically, let's say there are n stars here, and then you are calculating the potential, the force on a ith the stars due to the particle, and you can actually solve the equation of motion, just simple Newtonian equation of motion. But as you can like see, like this becomes like very complex term, the potential term, and this is no analytic solutions yet. Okay, so what we try to do is basically it becomes like an initial value problem, okay, for which you need a set of the initial sort of the position and the velocity to drive the system. Okay, so that's the essence of the n body simulations. And then there is a lot of sophistications like in this equation, the solving equation of motion, then calculating the potential, because you can do it for if you have 1,000 stars, 10,000 stars in the system, you can actually do a direct integration. Okay, it's although a bit time consuming, but you can do. But once you like cross a few million particles in the system, this becomes really uh, not an not a solvable thing, because the computer takes like enormous amount of time. It's not like days, months. It will be like more than several of months. Like you will not get into this. You can simply like look at like the some of the numbers, like put in the numbers. You think about like million. If you do direct sum, it's like n square method. So it's like the time will be like the huge. So we don't want to like get into there right now. So this is not there. But what we'll try to do, like let's say like we know that we know that like we need this, we don't have the potential. Okay, and both approach has like lot of difficulties, and we don't know how to like the, solve this problem apart from doing the brute force method. But but what I'll try to do is still give you some essence, like what we understand even without these things. Okay, even without it directly like the tackling the problem. Okay, a cartoon diagram shows that like here is like some Milky Way like galaxy in which the stars are like moving overall on a on a circular orbit, because it's a spiral galaxy. And in the box here where is the sun, around the sun, if you look at the stars, they seem to be going on a random orbit, if you look at from the point of view from the sun. Okay, of course, like the globally there is a ordered motion. So what we want to now like understand, that how do we understand the motion of the stars in a galaxy given a lot of unknowns in the thing. So one of the major unknowns that I'm going to talk about is here is the galactic potential. Okay, so that is the major unknown. So imagine you have a galaxy in which you know how the light is distributed, because we have talked about that light distribution. So it's like L, let's say like a function of R. But then from the light, if we want to know, is basically density. Like I'll go a bit back and forth. So from luminosity distributions, you want to know the surface density distribution, which is the mass density distributions. So for which you require a conversion factor. Okay, the mass to light ratio. That mass to light ratio, it seems to be an unknown. Okay, and then once you have the surface density, we want to like look at the total volume density of the galaxy, because what you see in the sky is a projection. Okay, we don't know the real shape, okay, real three-dimensional shape of the galaxy, because there is no way. Okay, right? So what we need from the surface density to go to the volume density, we need a deep projection. Okay, we need to know, we need to understand the deep projection, and the deep projection is again as a problem, because apart from sphere you cannot like know the uniquely do the deep projection. Okay, so there will be always like this uniqueness issue in the deep projection. So then the you can see that once we have the row, we can actually calculate the potential through the Green's function method. So and then what is lacking here is that the two stages of unknown thing going on. And apart from the unknown fact that the light itself could be we are not even seeing the total light and blah blah, all this stuff the possible, because maybe we have not gone enough to the the deep in the sky to get down the whatever we see here, we were talking about on that. Okay, so it you can see that the potential is itself is become very very difficult for an unknown quantity to derive from a galaxy. Okay, so there I don't think there is a way, because you can get a handle on the mass to light ratio, but the deep projection is yet unsolvable. Okay, deep projection is not it is not an easy quantity. As I said, apart from sphere, nothing is unique. So it becomes a issue. The mass to light ratio, to a good extent, one can estimate from various methods, like what is something called the stellar population analysis. One can actually get a handle on the mass to light ratio, but again these are all the gross quantity, because light must would also be at a different radius. Not have one mass to light ratio for the see some methods. Okay, okay. So let's say now with this unknown, let's say we have some. Hello.
Yes, sir. Go ahead.
No, there was some lot of noise came.
Yeah.
How is that possible?
Now it's fine. Go ahead, sir.
I know it's fine. Okay. The galactic potential, which is sort of unknown, but let's say we'll go with that, and let's say if we can write, for example, let's say consider an axis-symmetric potential in which the phi, the potential, does not depend on the azimuthal coordinate in the galaxy, because if you think about a galaxy like a spiral galaxy, is you go around at a given radius, if you go around the phi, there will be density change. Okay, and which will reflect in the potential as well. through the Poisson equation. So the Poisson equation can be like, sorry, the galactic potential could also depend on the azimuthal coordinate, but we sort of assume that the galaxy we are talking about here is a smooth and axisymmetric. So you can write the Hamiltonian of a star, and then you can write down the Hamiltonian equation in the radial, the vertical, and then the azimuthal. The azimuthal p phi dot, you can easily see that since the Hamiltonian does not depend on the phi coordinate, so this is equals to 0. So it gives you immediately the conserved quantity, which is the vertical component of the angular momentum of the star. Okay, and then from this you can actually show the r dot and the z dot is basically given by a very simple equation, which is like del phi effective by del r, z dot is del phi effective by del z. Okay, and then effective potential you have already come across has a potential and the centrifugal barrier, which is like Lz square by 2r square. Okay, so once you so this from the Hamiltonian of a star, you can easily get down to this r, capital R dot and z dot. Once you move ahead with this, you need to know the actual potential, because you want to solve these things numerically, for the orbit of the star. Okay, so that's but we don't know the potential. So what we do is basically we expand. So consider that the star is moving on a circular orbit. Let's consider that with an angular velocity the omega, and then we say, okay, about the circular orbit, we know what is the effective potential, phi effective, right? You can given an r equals to rg, which is at the circular orbit radius, and we can talk about the effective potential at that location. And then we say that we can now expand the effective potential in such a way that we say, okay, the stars is pushed a little distance in the radial directions, which is r minus rg, and in the vertical maybe about the z is equal to 0. Okay, so it's like a small oscillation kind of problem, and you can think about that the phi effective can be expanded in a Taylor expansion. Okay, and Taylor expansion about the circular orbit and at the location in the vertical direction. And if you do that, you very easily we'll see that the phi effective can be written in a very nicely with the two terms, one the kappa x square and the nu square z square. Okay, and this gives you the equation of motion, a very simple harmonic oscillator equation of motion in the radial direction and also in the vertical direction with the frequency kappa and nu. The kappa and nu is given by the second derivative of the effective potential estimated at the circular orbit radius. Okay, so this means what you see here is that, okay, the stars were going in a circular orbit at r equals to rg, and then you give a little push and the stars are basically oscillating with a certain frequency kappa, and in the vertical direction it oscillates with a vertical frequency. Okay, so it turns out that all these frequencies are all these three frequencies are the most fundamental quantity of a star in a galaxy. Okay, I'll give you a very schematic diagram of a rotation curve. You can see if you can derive later, and you see that this is vc and this is radius. In the inner part, the velocity is the circular velocity rises, let's say, linearly. So what you get here is the potential, which is proportional to r square, which is all derivable, from a very, very simple thing. And then you can have the kappa, which is actually twice the omega. In the outer part, when the rotation curve is flat, then you have kappa is square root of 2 into omega, which is the angular velocity, angular frequency. And the potential is proportional to log r. Okay, if the potential is falling or the circular velocity is falling like Keplerian, okay, the phi is 1 over r, and then kappa is actually omega. Okay, but in general, in a galaxy, this inequality is satisfied. The kappa is not, omega is not equals to kappa, not equals to nu. So all the three fundamental frequency of a star in a galaxy, they are not equal. However, if you have a Keplerian potential, like in planetary system, like in our solar system, which is very close to the Keplerian, then in that case, this inequality becomes equal. Okay, where the kappa equals to omega is omega equals to nu. Okay, so that's like something like the interesting so to keep in mind. Okay, that in a galaxy the fundamental frequency of the stars motion is not equal to, all of them are not equal to each other. Okay, so once you have understood that this star is actually going about the circular orbit in a radial oscillation and in the vertical oscillation, one can actually talk about the radial energy of the star under this approximation, which is called the epicyclic approximation. This is nothing but the kinetic energy plus the potential energy, and in the vertical direction also same. And it turns out that when you have a simple harmonic motion, this ER and EZ are actually conserved quantity. Means these are integrals of motion. This will not change if you go along the circular orbit. So if you go along the circular orbit of the star, so then this ER and EZ will be conserved, and you have a LZ conserved. So suddenly you have three conserved quantity in your hand. Okay, and these are very useful to construct the distribution function of stars in the galaxy. Now you can talk about, okay, I want to construct a galaxy in which all the stars are moving more or less on the circular orbit at r equals to rg, and it can change. And then you say that, well, now I want to say, okay, I want to construct a galaxy model under the epicyclic approximation. So at every radius you have a conserved quantity, and then you can sort of think about a distribution function for suddenly. So that's very useful. Okay, and then once you have the under the epicyclic approximations, you can also think about the calculating the total energy of the star. Okay, and this is the kinetic energy, this is the potential energy, and this inequality is another very important thing to remember if you are ever interested in knowing more than what I'm telling, is that the E should be greater than or equals to the phi effective. In other words, you will get from the phi effective, which is a function of R and Z, which is equals to less than or equals to E, would be some kind of a zero velocity curve. In other words, stars are restricted within this boundary. Within, but it cannot cross. Okay, it cannot cross the boundary. So the all the regions with the phi effective greater than equals to E is the forbidden to the star. Okay, so the stars are confined within that. There are also interesting thing, because you can also see that now the trajectory of the star in the epicyclic motion is, what is that? The small x, small y, which is basically some kind of a simple harmonic motion, and which is basically going around on a trailing ellipse about the circular orbit, and you have a potential phi effective is proportional to z square when you are very close to the plane of the galaxy, which is z equals to 0. Okay, in other words, if your small oscillations are naturally small, then you have actually vertical direction to some potential, and this gives you also any interesting quantity called the density close to the midplane is actually constant. Okay, but this may be true, this may be not true. One can verify in observation. There is no this is the anyway approximation. So, but if you see the density is sort of constant, it's not changing very dramatically. Okay, then I think you can think about okay, maybe the potential is actually the stars are on an epicyclic motion, which is in the vertical direction. So this is a useful quantity to check. Okay, so far what we have done is that the stars are moving on a axisymmetric potential. In an axisymmetric potential, when there is no non-axisymmetric term, okay, the LZ become conserved, and then the phi is as well which is a function of R and Z is independent of the phi. Okay, now the real galactic potential or real galaxies are much more complex. This picture I kept showing, and there this is nowhere axisymmetry. Okay, you go around at a given radius, the potential will keep changing. Okay, the density will change and the potential will change. So the phi is actually the function of the three coordinates x, y, z, or the r, phi, and z. Okay, not only that, it may depend even on time. The potential becomes time dependent. So then, like, you are totally gone. Like, this is will be like really difficult problem, because this is like the next step is the phi, which is like depends on the azimuthal coordinate, and then you have a time. And how does the time dependent comes into picture? You see these images, because I may not have time to like look at this all the time. So if you look at the central structure, the bar or the spiral arm that you see in a galaxy, like spiral galaxy, like our Milky Way, these structures are rotating. Okay, the bar is rotating with its own pattern speed. Okay, it's like a fixed pattern rotating. So do the spiral arm. This is with a fixed pattern. The frequency with which they move, the bar and the spiral, they may not be equal. Okay, they may not be equal. So then you have like actually like one pattern, you have another pattern, you may have like multiple pattern in the galaxy. Okay, for example, you saw an example of a nested bar which I saw yesterday. So you have a bar and then within another bar, the two bar is rotating with a different pattern rotation, different pattern frequency, and then you have actually two time dependence in the system. And then if you have a spiral, you have three time dependence in the system. Means like it is not possible now to go into the idea is basically like why I'm talking about this. These time dependence are actually time dependence through the rotation. Okay, so it's like a frequency, it's like a pattern which is moving or rotating in the galaxy on top of the background of the stars. Okay, on top of the background of the stars are moving its own velocity depending on the potential, and this pattern is rotating on top of that. Okay, so then this introduces us some extra time dependence in that. Okay, if you have one time dependence, you can like change going from phi to t, like the phi prime with a phi prime minus omega into t, where omega is the pattern frequency. You can actually eradicate or remove the time dependence from the potential. Okay, for example, if you have a one pattern which is rotating with a certain frequency, you can go into that rotating frame and say, okay, like we are like sort of removing the time dependence, and apart from by considering the Coriolis force and then the rest, and but if you have a multiple pattern, you really difficult, and that's like the problem. And most realistic systems are actually like this, where you have a multiple pattern and then the potential is never axisymmetric. And the same could be true even in a small elliptical galaxy. The small elliptical galaxy have certain amount of rotation. I will show you like the some images, like beautiful one. Okay, so having said that, I will go into a little like detail here, but not too much. So I wanted to show you that once you like go into a like sort of like the, let's say like a barred galaxy, okay, and you can have the potential which is like the based on the axisymmetric part, and then you have a potential which is the perturbing potential due to the bar, for example. Okay, the phi 1 r could be a cos of m5, m equals to 2 is a bar. In this kind of potential, what you have is basically you have the Lagrange points, okay, the stationary points. This gives you like some kind of a the guide to understand this system, because when you have time dependence into the system, then you do not have the conserved quantities. Okay, in this particular case, if you have a one time dependence, I do not know if I can show you later. Yeah, I think I'll talk about that. If you have a one time dependence in the system, so you can go into the rotating frame, and and you will see, you can write down the equation of motion, which is r double dot equals to minus gradient of phi, and this is the omega p is the pattern frequency of the pattern, let's say it's a bar or spiral arm, and this is the centrifugal and the Coriolis force term. One can show that in this system, neither energy nor the angular momentum itself themselves are conserved. Okay, but a combined quantity which is composed of the energy and the angular momentum, where omega p is the frame's frequency, like the so as I said, like the bar could be rotating with a pattern frequency. You can go into that frame and like construct a quantity called the Jacobi integral. So this Jacobi integral becomes a conserved quantity. Now this is for one time dependence, because if you have another time dependence, you don't have this even Jacobi integral concept. Then you have totally the system which is free floating in some sense, because not even the energy is conserved, and then not the angular momentum. Now you don't have a Jacobi integral, so you don't have. How do you evolve the system? How do you understand? Like, because what is the guide? Guide in a sense, when you evolve a system, you need something like, hey, look, I evolve the system such a way that my energy is conserved. Okay, so you can say that. But when your energy is not conserved, how will you sort of know that what's happening in the system? So that's a difficulty. So I will so once you have this, like as I said, the Jacobi integral, which is like a conserved quantity, once you get that, one can actually like now look at the effective potential. Now the effective potential is when the effective potential equals like 0, which is basically the force. Then you actually can construct like the Lagrange points. Okay, so these are basically Lagrange points are basically nothing but where where delta, the gradient of the effective potential equals to 0 in the system. And so we have in a galaxy sort of L1, L2, and L4, L5, and L3 is at the center. So these are like the 5 Lagrange points in the system. So these Lagrange points are like kind of important. So we'll talk about that. So to give you like a little bit more onto the like what kind of like the motion of the stars that we expect in a system. Okay, so imagine like you have a potential which is the effective potential, which is like this. The phi effective is basically the logarithm of like an x square plus y square by q square. Now you can see this, because of this 1 over q, this is actually non-axisymmetric. Okay, and then you have a centrifugal force term. Okay, so you have, this is basically the effective potential that we're talking about in this. So you can like look at this sort of effective potential and look at the orbit of the stars in this kind of potential. So it turns out that like there are like in the center of the galaxy you have often the box orbits. Okay, in the outer part of the galaxy you have the loop orbit. Okay, loop orbit are like this is one section, by the way, but this is a three-dimensional picture. The loop orbit, this is like sort of like the integration. So you can take this kind of potential which I talked about, and then launch a star in the y direction, let's say. Okay, with a velocity, you can get into like this kind of a loop orbit. So it's important, how do you launch a star in a galaxy to construct like the loop orbit. The loop orbit is not closed. So for example, if you can go on like this, and once it like finish one like sort of, let's say it starts from like the x is equal to y is equal to 0 and x is equal to some like number here, and then it will go on, it will not come back to the same place, because the inherent frequency, the three frequencies are not same. In the plane you have a circular frequency and the radial frequency which are not same, so they are not commensurate. Okay, that's why they don't close. It's like your Lissajous like figure. Okay, So what happens is that because of which the orbit will keep on going like that, and over a longer period of time, it forms like a tube. This tube, if you think about that, there is a if we, the one approximation of this is basically a circular, the closed loop orbit. That's a circular orbit. So the circular orbit is actually a special case of loop orbit in a galaxy. It's a special case of loop orbit. And then the depending on the launch, there can be various kinds of orbital configuration possible. For example, the same potential in which it can have a banana kind of orbit. Okay, on the bottom line, I'm not showing you because these are like the approximation of this, the representation of the orbit, because these orbits are like three-dimensional. Okay, so this is the cross sections of that in the or in a best way you can see that the motion of the stars is six-dimensional, and you want to look at you can't view the six dimension, so you want to look at the cross sections of that. So this is one such cross section. This is y and by. Okay, so this is called the phase space, or the cross sections, or the Poincare cross section. So depending on certain there can be sort of banana orbits, and then also there can be the fish orbits. You can join this up and down together and form an x kind of shape here. Okay, x kind of shape here. And so orbits are in any way, there can be you can make a millions of the orbits in a galaxy. Okay, and this is a fun thing to do actually, if you like it, because once you have these orbits, you can these are like a backbone. It's like a bricks in the for the galaxy. So the one thinking in which people say that the galaxies are nothing but in a given potential is made up of orbits, and then some stars populate the orbit, some stars some orbits don't get populated. So depends on certain instability and stuff like that. So if we can calculate lots of these kind of orbits, one can create various structures in the systems. You can merge together. There are ways to do that. Okay, for example, if you see this loop orbit, I can think about a nested loop orbit in the plane, and I can say, okay, this is how the basic galaxy is. The galaxy is just a set of circular orbit, but the circular orbit is very unstable. Okay, only circular orbit is very unstable, but you can have a loop orbits and then stack together this loop orbit, concentric loop orbits, and you can make a a planar galaxy. Okay, and if you can orient it differently, you can make a different structure. So this is the beauty of this understanding the orbits in a galaxy, and one can actually construct many different kind of models based on, because these are all there are real stuff, because this is you integrate the equation of motions and you have the guideline. Okay, so this is a useful quantity. And the orbits actually also if you project this orbit, it's a face on, and then if you project it, you will know that the stars will go in one direction into the y, and then coming out of the y. So there will be two velocities. Okay, so these are becoming much more important to sort of understand, and so orbits gives you an idea about the motion of the stars actually. Okay? So the motion of the stars. And then I think I didn't have a time to look, but similar thing I would say that this is I've already talked about the how do you calculate the Lagrange points. So the important thing that if you have heard about the Lagrange points, and you in other contexts, for example in the Sun Moon Earth system, the three particle system, this is a similar thing actually. Basic philosophy is same. So this is how you calculate the stationary points in the galaxy. But then one can ask so what do you understand from the stationary points of the galaxy? So stationary points of the galaxy give you a sort of space where you can actually think about the constructing the system. because rest of the place you don't have the energy integral, which is like the conserved. Okay, so stationary points are in some sense like the very useful guide. Okay. um, um, okay, so I'll quickly show you a bit more onto the some orbital structure which is you can look at this paper, the Selwood and Wilkinson, and it's like bit old paper, but it gives you a lot of basic things, like for example some of the periodic orbits, what I was talking about. These are like set of circular orbits. These are actually kind of loop orbits. Okay, and then you see the orbit which looks elongated. This gives you the sense of a bar. Okay, so in a bar there are many different kind of orbits are possible. Okay, and there can be this is the 1x1 orbit, this is the x2 orbit which is perpendicular to the x1, and then you have higher order different orbits. What is important in this is that if you have many of these orbits in a barred galaxy potential, often you can see that the large fractions of the orbits are actually chaotic. So what is what is here, what you see here, this plot is not good, is again y versus vy, and this is the Poincare surface of sections. These are the circles, concentric circles that you see. These are actually the loop orbit in the bar potential. Okay, these are the loop orbits, and then loop orbits are actually at a higher and then I'll give you very for example, if you take this, and if you construct a phase space out of it, as as I said, in the periodic, when you have a this orbit is not periodic, first of all. Okay, because they don't meet each other after even n turns. But one approximation of this would be the closed circular loop orbit. Okay, the closed circular loop orbit will be projected as a point in the system. If you have a circular, like the width will shrink and shrink, and when you have a purely circular orbit, you will get a point here at the center. So that's the kind of orbit. So it turns out in the bar potential there is no such thing. Okay, there is no such thing like no circular orbit totally. Okay, the in bar potential, because of this the elongation, there is no circular orbit, and the angular momentum is always much less than the circular orbit. But you have many dots here. You see these dots don't meet, these are not periodic. Okay, and these are actually the chaotic orbits, so they are spread around everywhere in the phase space. So it turns out that there is a lot of orbits, or the stars, a good fraction of the stars in a such a bar galaxy potential are actually chaotic orbit. Okay, I think I should stop. I'll continue tomorrow from here only. Okay, so we'll talk about tomorrow the real measurements of the velocity, and how do you measure the velocity dispersion, and what can you do from the direct measurements. Okay, so the sort of theoretical part is over today, for up to this part. So I'll stop here. If there's any question. Hello? Sagar? Santosh?
Santosh is not here, sir.
Oh, okay.
Just
Sir,
open.
Sagar?
Just open your chat box.
Okay. If someone wants to ask a question, no. Hello.
Kanak, there are some hand raised, so you can unmute them.
How can I?
Can go to the participants in the
Okay.
down. Like
Okay.
there will be some hand raise,
Unmute.
hand
Okay.
raise, and
Who
decide
do I
that you can.
unmute first?
Yeah, you can unmute any one of them, and they
Okay.
can answer.
Okay.
Hello.
You can speak Junik Sengupta.
Hello, sir. Good morning.
Morning.
Sir, am I audible?
Yes.
Thank you, sir. Sir, actually, I have a question regarding the initial parts of your slides. The star distribution function. The distribution function of the stars is dependent on position, velocity, and time.
Yes, the
So-
phase space coordinate. Yes.
Yeah. So, would you please can you please elaborate this thing a bit? Like, how is it dependent on position, velocity, and time at a particular point, and what is its actual significance?
Yes, so the distribution function, the physical significance of this is basically for example, the stars when it move in like in a galaxy, it has a 3 position coordinate, right? And it has like also like 3 velocity, bx, by, vz, and xyz coordinate, isn't it?
Yeah. Okay.
So this is basically the phase space in some sense. So I want to like know, so now if we consider some infinitesimal small volume element in this 6-dimensional phase space, so you can compute the number of stars in some sense, okay? And then the number of stars divided by the volume will give you the like number density. Okay, so in the limit, this infinitesimal volume goes to like 0. This gives you like some definition of the distribution function.
Okay.
So the physical significance of the distribution function is that it basically tells you like the number of the stars in some sense in a infinitesimal phase space volume.
Okay, so it's like that we are considering a particular volume element in space, and then we are
In the phase
checking
space.
the number of stars in a free space. Okay.
Yes, in the phase space.
And we are checking the number of stars in
integrate
that
over
point.
all velocity. If you integrate over all velocity, you get the number density of the stars in the galaxy full.
Okay.
Okay.
Okay, so it's like that we are initially taking a small part, and then we are integrating it to get the number density in all over the galaxy.
Yeah, the significance is that the density, number density of the stars is equal to integral of the phase space, the distribution function over all velocity.
Okay, sir.
Okay, bx by vz. Bx by goes to from the all like the allowed like the limit.
Okay. Thank you, sir.
Yeah.
And sir, can I have a second question, please?
I don't know what is the rule. So there's another person. So if it is quick, then please go ahead.
Yeah, it's like that. Can you please refer to some study materials for this purpose?
I think I have given one reference there. It's like there is a book by Galactic Dynamics by Binny and Remain. That has a lot of details in it.
Okay, sir.
Okay, Galactic Dynamics.
Thank you, sir.
Okay, I'm unmuting Himadri Saha.
Hello, sir.
Yes, Himadri.
Sir, when you have considered the rotating system of the galaxy, so there is a force balancing equation you have shown that we consider potential gradient and centrifugal force. But sir, my question is why we are considering Coriolis force? Does Coriolis force have any effect on the rotation of the stars?
Oh, you see, the stars are rotating because they are going around the galaxy.
Yes, sir.
Okay. Now you are adding an extra potential, which is like rotating potential. So if
That is
you
considered.
yeah, so if we go to the rotating potential in a rotating frame, like you have this Coriolis force. So
Okay.
the stars are, as I said, like they are going around the galaxy even without the like rotating potential. But if you have a rotating potential added to that, so that will add to like they will try to like drag stars around each other, around them. So the physically like there will be an effect of that. It's like a similar, if you want to understand the like motion of the like the air in an earth, like you see how it is, right? It's the same.
Sir. Okay, thank you, sir.
Hello. How do I get to these questions like? Hello.
Yes, Kanak.
Um,
Yes, Kanak.
Sagar, there is a chat box here. So
Yeah.
to answer this chat box, what do we do like generally? So do you have
So
any?
you can read up the questions and the person who asked, and then you
Ah.
can answer them.
Okay. Okay.
You can select some of the questions from there. And
Okay. Okay. You have answered that. Is this guy possible? Arjun Dawn? Arjun Dawn. Can Arjun Dawn hear me? No.
Yes, sir. He is here.
He's here?
Yeah.
Okay.
Arjun, can you raise your hand?
Okay. Unmute. Is your mic working, Arjun? No.
No.
Okay. So your question was like, when we are doing n-body simulation in the potential term, we consider gravitational potential. Does the expansion of the universe not affect it? Yes. The question is the n-body simulation that we are doing, that I was talking about, that is an isolated system. Okay. In an isolated system, we don't consider the expansion of the universe into account. But there are simulations when people do the simulations of the universe. Okay. In other words, they simulate a patch of the sky, like the full universe, like the cosmological n-body simulations. They do consider the expansion of the universe into it. Okay. So there is that is a full scale, like the simulations. All right. Madhusudan Purohit, are you there? If you there, can you raise your hand? Madhusudan Purohit.
He is here, but his mic is not working.
Mic is not working, but
Yeah.
is he listening? So
Yeah.
okay. You said that you asked what is the probability function of collision of any star with some other stars in a galaxy. Okay. So this question can be answered. For example, within the framework that we talked about, the the collisional probability and all this stuff, we have actually dropped it. Okay, we have actually dropped it because we talked about the collisionless system. Okay, but if you are actually interested, look at something called the BBKG hierarchy. Okay, in that you will be able to get a detailed sort of account of the how to the understand the what is the probability of collision, because I have already shown that the collision probability is the 0, but way to do is basically the collision probability is the through the distribution function. Okay, so how do I if you do you see that in the first sort of the slide that I shared, in that I have naively written that the mean free path, the calculations, and the collisional probability. Okay, that should give you the answer for this the kind of question that you are asking. Okay, so from there you can you should be able to, if you know the mean free path calculation. Okay, the same thing you follow with the right hand side of the slide that I have shown, and in that you will see that using the mean free path one can actually talk about the collisional probability. So it is actually comes from a if you are interested only in to know the what is the probability function. Okay, so the way to construct is basically through that. So you should go look at the mean free path calculations either in statistical mechanics or thermodynamics, and basically look at the plug in the numbers that I have given. You will get the probability function from there. Okay. Was Agam Kumar Jha? Are you able to hear me? Agam Kumar Jha.
Yes, sir.
Can you hear me?
Yeah, I'm hearing you.
So your question is, in CBE equation, you have taken reciprocal of position vector and velocity vector.
Yeah, distribution function with the function of position and the velocity, and in the partial differential equation you have taken the reciprocal of position and the velocity.
Where just a moment.
Yeah, just go through after the material derivative.
In the first slide.
Yeah. So here, this is the x vector and the v vector in the equation. If the flow is Hamiltonian, then you have written down a partial
yes,
differential
x
equation.
and v. Okay, it should be like a r and v.
Yeah, and also velocity, can't we have the reciprocal of the
what is
vector?
Reciprocal you mean here?
This is, you have taken, how you can have this x vector and v vector in this. This would be the r. Yeah,
derivative. This should have been del f by del r vector.
Yeah.
So it should be bx into del. He said the vector. You have to do it in a vector way. It's actually the gradient of f, the material gradient of f.
Yeah, with respect to position.
With respect to position, exactly.
Yeah.
Okay, and then there is another the material gradient of f with respect to the velocity, the last term.
Yeah.
Okay, so is this clear to you?
Yeah. Actually, I got confused with this vector sign. Okay. Because we can't have,
Okay, no, this is not x. This is
yeah.
This should be r, and this should be a material gradient of f. But
yes.
This is okay. I could write v dot del f del r and then del f del b. Okay.
Hey, Kanak, the next lecture will start in 10 minutes. So,
Is it?
yes.
Okay. Sure, I think I should stop then.